nanohub.org.
Online simulation and more for nanotechnology.
Your principal presenter today is Dr. Alexandra, I'm going to say this wrong,
Boltasseva.
Sarah. Although if she stumbles, her postdocs, Alice and Michelle, are here. They assured me that if they catch Mom in any mistakes, they will politely step in and correct. But thank you. She comes to us from there is no typical pattern, except that every faculty member here has a fascinating history, and yours starts in Moscow or somewhere, Moscow University, by way of Denmark. And happily, Purdue has landed her. So you're part of a great faculty family.
Thank you.
And we're delighted to have you here today. Thank you for sharing your work with us.
Thank you, Mitch. Thank you. And really thank everyone for coming, and thank you for inviting, because that's the greatest honor one can have and greatest recognition to be able actually to share with you what we are doing and what we are excited about. So I will be talking about optical technologies and what we do at Purdue and how we want to make light work for us at nanoscale to enable the next generation of and faster computing, communication, energy, and biomed. Well, this talk was announced as being very scientific, but I will bring some history and hopefully some interesting facts into it as well when I speak about a brief history of optics and optical technologies. And then I will try to explain why we want to go into optical technologies, why we want to expand them. And after all, why we want to go nano there? Why do you want to bring light down to nanoscale? And even if you want to do that, what are the challenges? Well, obviously, we would need some kind of exotic technology to do that, because nowadays all the lighting and we have around us is not really nanoscale. And so I will tell you about this exotic approach that's called PLASMONICS. And as every new emerging technologies, it has challenges and it has solutions. And I will talk about both of those and show you some examples of the devices and functionalities that we are pushing for. And specifically, one of the most technologically driven area of this exciting research direction, as I look at it, is in optical skins and smart coatings that would be able of communicating, sensing, camouflaging, and many, many more. So let's start by saying that 2015 was announced to be the International Year of Light and was dedicated to the optical technologies and how they provide solution to big challenges we have around us in communication, computing, energy, education, agriculture, and health. So you may ask, why 2015? And actually someone found, and someone is a good colleague of us back in UK, that dated back 1,000 years ago, in 1015, there was the very first book that's considered to be the book of optics. And so Al-Hazim actually was not just introducing optics, he introduced the scientific methods as we are applying nowadays to optical technologies. And you might not notice, but the optical technologies are all around us, not only in the optical communication systems that literally changed the world we are living at, but also in health, hospitals and the beauty industry, energy, solar panels. We see them every time we go to Indianapolis Airport. Economy, which is driven very much by the information technology and our ever hunger for packaging information more densely. Environment, we are using a deep water microscope to study the flora and fauna, and agriculture for sensing, and of course social media. So, but if you look at the beginning, it started with a lens. So everyone is using lens, maybe if not every day, but very often. And the oldest lens in the world is actually the Nimrod lens, 4,500 years ago. If we look back and 1,000 years ago, we say that the scientific method started to develop and people discovered the law of refraction, known also as a Snell floor. Well, let's go back to nowadays, and it's interesting to notice that we are still using the same basic laws. So we haven't really moved very far from the law of refraction. Well, think about refracting light by a prism or a lens, or diffraction, where light of different colors actually goes in slightly different directions depending on the color and the microstructure. So you see the diffraction every time you take a CD or DVD out, and it has a rainbow colors in it. Or, to that matter, reflection. That will be used in actually one of the most enabling technology where light can be confined and bouncing back and forth inside a high dielectric or optically dense material. So this basic laws paves the way to technologies we have around us at the moment. Microscopy, microscope, telescopes, spectrometers, the whole realm of diffractive optics for a range of applications, mirrors, of course, we're using it every day, and optical fibers or integrated optics. So with this said, my question to the audience would be to guess, what do you think were the most impactful, historically, event or discovery in optics? Well, if someone is thinking, yes?
Lasers?
Lasers, well, perfect. But lasers came much later. And actually the historic impact of optics is actually the pasteurization and the surge system we have in every city. We wouldn't be around here if Louis Pasteur, back in 19th century, wouldn't have discovered, using his microscope, that microbes are cause of diseases, and actually the food spoils because of microorganisms. So, and it's all because we had microscopy, that we had lenses. Well, being more serious, let's come back to the technology we have around us now. And, of course, the invention of laser. So there are many Nobel Prizes in physics that are related to optical or technologies that are built around it. So if this is, of course, a selection of Nobel Prizes. There are many more related to optics. However, if we look at all this, and some of them you notice are on materials like semiconductors and blue LED, some of them are on truly optical topics. So what really unites those selected topics that people got Nobel Prizes for is that they are being used or already enabled information technologies. Information technologies are the technology that we have all around us, and the ever-increasing need for faster information processing and faster information exchange is undeniable. You know, there are no teenagers that spend a day without Snapchatting, or the little ones without YouTube videos, so we are hungry still for faster communication and more bandwidth. But, you know, exponential growth cannot continue forever. So, what is really going on? Where are we? And what really enabled the transformative impact of optical technology on the society we have around us now? And the question for that is that people did realize that in order to make things faster, you have to use the fastest messenger that exists in nature. And the fastest messenger is a photon. So you have to use light to transmit your signals or information. And it boils down to the frequency of operating frequency. If you compare with electronics, and that's here, sorry, we're getting a little more technical, but you're operating at the gigahertz range. And if you want to really push the technology further, to harness the beauty of a faster communication systems, you have to go way up higher by using photonics. Electronics, you can say, well, electronics is so well developed, why don't we just push it further? Well, unfortunately, there's a fundamental limit that hinders the speed increase, and it's connected to the way the circuitry is built, resistive capacitive effects, so-called RC delays. And indeed, if we look at the chart of the operational speed of different technologies for data transporting, well, we started with a telegraph. That was extremely slow, maybe one line, you know, that you can transmit. We telephone, and then we got the coaxial transcontinental cables. That was a huge advancement. But really what we will see that electronics really is running out of steam due to these delays, and we are close to the saturation with the small chips, the CMOS chip that we have. And photonics indeed is offering us tremendous speed increase. So let's go back to this electronics versus photonics competition. And this is an exercise I give to my students in Introduction to Engineering Optics. And I ask, well, how many audio channels you think we can transmit over a signal of about 2 gigahertz? So this is actually a 4G cell phone signal. And if you do this exercise, you actually say that, well, it would be around 300. Now, again, it boils down to what you want to hear in iTunes and things, and we all want more, we want streaming. So what happens if you ask the same question and say that now my information is transmitted over optical cable? And the optical cable uses light. So at a slightly longer frequency, wavelengths that are visible light, 1.3 micron, the answer would be 36 million channels. So maybe you don't need it right now, but right at this moment, but if you ask teenagers, they want all the bandwidth they can get. And the more, the better. Okay, so it's easy. Just replace everything with photonics. We go all optical. After all the information we learn about the world is optical. Why do we want to have the electronics links at all? Well, and we were sort of on the way. So when we talk about the long-haul communication systems, coaxial cables are replaced by optical fibers. And thanks heaven, even in West Lafayette, we have Metronet with optical cables now entering homes. So my dad is always saying that I retired him because he was an engineer working with coaxial cables and electronics. And he said, you know, when the first equipment with optical cables came in, I said, I'm gonna retire. I cannot just, you know, go in and see where my signal is because it's completely different regime. So you are engineers of the future, so thanks for retiring me. We already did that. So what would be the next step? The next step would be if you say, I want to do it all optical, you really want to increase the speed of the information processing, not only transfer, right? You go down to a chip. So now the chips are really small. You are dealing with component sizes on the order of tens of nanometers. And people have tried already for a couple of decades to replace electronics with on-chip optics. So it means that you are scaling optics down. You take your optical fibers that may be micron size large and want to bring them down to this nanometer scale. So we've been very successful in replacing coaxial cables and transmitting information with light. But when it comes down to really processing and information exchange on a shorter distance on chip, we are not there yet. And the reason for that is that we do have a diffraction limit that sets the size of the smallest spot you can focus your light in. So it sets the limit of how small your waveguide can be. You can think about the wavelength of light, which is large, and you want to, you know, squeeze it into the nanometer size. Diffraction says, oh no, if you want to focus your light, you will be limited to the wavelengths of light at large. Okay, so we are in the need of a new approaches to really match, you know, this discrepancy. So photonics is fast by really large component size, and then electronics is slow, but it's very, very compact. So, and there is a missing link, apparently. So if we look at the operating regimes of different technologies, again, here's your electronics, extremely compact, but limited in speed. And here's your photonics, here's your optical fibers that are really fast, but the size is greater than 1 micron. So this missing link, that the solution to this size compatibility problem is really plasmonics that I will be talking about today. Another way to think about this, this need for nanoscale optics is to look at so-called Moore's law. I mean, it has many faces. And one simple way to think about it is that every 18 months the computer power would double, so you really have to get faster in processing it. And if we look at the dimensions that we're involved in computers, it's very clear that you have to do it optically to get it faster, and you have to go down to nanoscale. Okay, so what are we going to do now? Here's the wavelengths, here's your light. which with a wavelength of about half to 1 micron. Really big compared to about 50 nanometers. That's where you want to get if you want to, have your all optical integrated chip. But it's a problem because light with such a big wavelength, it doesn't want to notice very small features. So if you just make a nanostructured material like this out of, glass or something, light will just pass around, and over the wavelengths of light, it will sort of feel some kind of average effect. So there will be no fancy stuff happening here. Well, unless you start thinking about unconventional materials that you can use in optics. So if you go back, you reflect over lenses and fibers. These are all transparent materials like a window glass. Optical fiber is also glass, so light is propagating in something which is transparent. So it turned out that to bring light down to nanoscale, you have to look at metals. Well, now we know metals. These are our mirrors. Aluminum foil is totally reflective. So what can happen at nanoscale with a bad optical materials that reflects all light which is incident on it? And wonderful thing happens if you take a metallic particle of the nanoscale dimension. It's so small that actually it doesn't act as a mirror anymore because it's just too small for it. There are no wave propagating effects. But what do we have? Metal is a conductor, so there are a lot of free electrons inside. So what really happens when your light or electromagnetic wave is incident on such a particle, the cloud of free electrons, they're free to move. That's why they're conductors. They start to oscillate in a collective manner, creating the tiniest antenna in nature. So this tiniest antenna would be resonating at the optical frequency, but the size of it would be just tens of nanometers. So these nanostructures, like if you bring two nanostructures together, this is something that actually we did, so you can bring them very close to each other, and it turns out that the light would, or this coupled oscillation would create tiniest localized spot of light. But the size of this so-called hot spot will now be of about 10 nanometers and will be dictated by the size of your nanoscale metal particle. So such an optical nanoantennas in plasmonics have been proposed for imaging, sensing, photothermal therapy, and energy application, and quantum photonics as well. So the name for this field is plasmonics because the name for these oscillations that we are exciting as surface plasmons. So the surface plasmon can be localized as dictated by the nanoparticles. And if we look at what they can actually bring, there are many different things. So at Purdue, we spent a lot of time studying effects of these plasmonic nanoparticles for applications in just reaching the high localization of the field, but also in sensing application in collaboration with Alex Way. When it comes to nanoparticles, then the best example of an exotic thing that you can accomplish is actually work by, my colleague and husband, Vlad Shalaev, in collaboration with NSU and Cornell on demonstrating the world's smallest nanolasers. So this is just, again, a metallic nanoparticles coupled with some kind of gain material. So it's only 22 nanometers, but it acts, or you can be considered like a very small laser. Then, and later on, this concept was developed at Berkeley into something that you can actually integrate on chip. So these nanoparticles that really resonate at optical frequencies and have this strong interaction with light, you can put them together. You can put them together and you can vary the size and the shape of these nanoparticles. And like a miracle, if you put them all together, they create an optical material which has properties very different from the materials you started with. And that is the field of optical metamaterials, where the properties of this exotic new composite optical materials are actually dictated by those tiniest resonances inside. So one of the interesting things is that you can tailor the optical properties of these artificial materials almost at will. Whatever you want to do, well, in principle, can be achieved by the proper design. You can achieve negative refraction. And by the way, the first optical negative refractive index material was created here at Purdue in 2005, and by my colleague Vlad Shalaev. And you can do other exotic things. I don't have time to name them all. For example, an optical black hole, where all light is just sucked in, doesn't matter where it comes from, what doesn't matter where the wavelength is. And proposed, by the way, by my Purdue colleagues, Professors Narimanov and Kildashev. So going further from there, you can actually say that by using the same concept of matter surfaces, now I go further and I say, I want to do something which is extremely thin because my nanoparticles are tiny. So if I'm using just a monolayer of this matter material, I will be using so-called matter surfaces that can do wonders, being just one monolayer thick. And I will show you example of functionalities further in this talk. Okay, so but one of the examples that is really that I use as my cover image is indeed a matter surface. So it's just a nanostructured layer of gold, which is just 30 nanometers thin, but it would act as a hologram we know today. Okay, another big area of this exciting field is where not only you confine light to the nanoscale, but you also propagate it. So we have to keep in mind that one of the motivations is actually to create this all-optical chip. So it turned out that the propagating surface plasmon waves can exist at the interface between the metal and dielectric. They would be confined in a vertical direction so that you indeed can squeeze light down to the scale, which would be inaccessible with optical fibers. So if every time you use a waveguide which is made of dielectric materials, you will be facing the diffraction limit. But not here. It's a completely different principle, and they can actually pave the way to a circuitry that you can interface both with photonics, we will have optical fibers in, and optoelectronics, or electronics to that matter, that you can have integrated on the same chip. Comes from our collaborators in ETH Zurich. Okay, so problem solved. We have a technology to scale it down. Everything works. There has been, all the components have been proposed in studies. Not really. Nothing comes for free. And every technology has its challenges. So the challenge for this technology is the same as its benefit, right? Because when you think about this oscillation, this free electrons is really the key. You have to have them in order to enable this resonant behavior and couple light, or hold light at the nanoscale. But when you're using metals to do that, and in most cases we're actually using precious metals like gold and silver because they have the best properties that we need. So when we are using it, a lot of light is lost. You cannot go around the ohmic losses, unfortunately. The last light would be lost. Every time electrons move, part of the energy goes to loss. So if you have a waveguide, it can be super confined, but the intensity of the light would be decreasing way too fast that you want for communication systems on a chip. Okay, and other problems. Well, metals are really hard to process. They form islands, they don't want to grow with thin films. And what's most important for the integrated optics is that metals, or noble metals, are poisonous to semiconductor industry. So for those who are not familiar with the whole CMOS process, I can just say that having gold next to a semiconductor like gallium arsenide can lead to completely destroying the function of this device because gold will diffuse inside and ruin whatever functionality you have. And they are actually soft metals. All those wearing, jewelry, silver covered with gold, know that gold disappears with time. Most importantly, it has a low melting point and it's expensive. So there are way too many problems with that to have a technology ready out of that. So, but there's challenges, always come solutions. So what should we do? There are different ways to go around it. The first way that you can take is that to say, you know what? My loss is not really a problem. I'm gonna design a system where I will use this loss for good. So turning loss into gain is a big activity that unites several, people at our nanophotonics group. And one of the demonstrations of how we want to do that is going to appear in Nature in 2 days, April 26th. And Kayla is right here with a press release. And I said, is it okay to talk about it? So probably it's okay. You're not going to, shout after the seminar that this is what they did. But what we really showed is that you can indeed use the best of two different worlds. You can propagate your light using transparent materials so that we are not limited to this absorption or loss in metals, but you can have still a metallic or plasmonic components on top of your waveguide such that when you want to switch your signal off, it couples to this metallic mode. So now what we call a plasmon-assisted electro-optic modulator would be an essential piece in a circuitry. So what modulator does is to switch your light on and off. This is zeros and ones that ultimately you want to do for your processing. So yes, having combined the loss of the plasmonics and the compactness of it will actually help us to demonstrate both high speed, because we are using optics for transmitting signal, but also extremely compact optical modulator. Now, another example of how to use loss and turn it into gain is to say, well, you know what? I'm focusing light down to nanoscale with a nano antenna. I'm getting my hot spot of 10 nanometers, and I just want to heat it up. I want to heat it up as much as I can. And this heating can be combined with either fluid motion because of the temperature difference and with optical trapping or optical tweezers. So optical tweezers have been used in many technologies. So you're using focused light to actually hold your, say, particles in place. So you can expand it to nanoscale by combining the nanoscale hotspots with the idea of actually trapping the particles and holding them there. So my brilliant student, Justice Ndukofi, who is just an assistant professor now at Vanderbilt, proposed this idea with the optofluidic group at Purdue, led by Steve Verrilli, and demonstrated that indeed not only we can trap and hold the particles with a nanometer precision, you can actually use for future nanomanufacturing approaches as well. Okay. But there is still a problem. As I said, if you focus light down to nanoscale, optical trapping or not, things heat up. And the problem is really that the field confinement is so high that even metals like gold and silver that have a high melting temperature would be destroyed. So part of this is that the melting point in nanostructured material is much smaller. So it's enough to heat it up to 300 or 400 degrees to see that your gold structure is completely ruined. Inherently, in this area of science, every time we shine the light into this tiniest metal nanoparticles, local temperature goes up. So, and in addition, as I said, we have to find materials that would be compatible with the circuitry. Okay, we look back at the silicon industry and said, you know what? Why are we just limited to metals or noble metals? Why don't we look broader? So if you look at the progress in the silicon technology, in the 80s, they started just by using a few elements of periodic tables in their chips. Nowadays, it's almost all periodic table is present. Depending on the functionality you want to get, whether it's a wiring or any other elements, you select the proper element. And that's the activity we started at Purdue quite some years ago, actually in collaboration with Team Science, who is an expert in material science. So we said, why don't we expand the parameters? But why don't we look at constituent materials that could actually help us to enable the new applications for plasmonics? Maybe they will offer some benefits over noble metals. And this is created by my another brilliant student, Nate Kinsey, who is assistant professor at VCU now, Well, we say we started with plasmonic metals in yellow, and we expanded it now to so many compounds that can be used and enable functionalities we need. Let me give you the first example. By looking at the church as a Russian-born, I have to talk about, it was a pleasure to show this beautiful domes of Russian churches, but actually, all that glitters need not be gold. And it's not gold. Kremlin, I guess, the only place where they covered in real gold, but this is really titanium nitride. And you can cover your roof with titanium nitride for essentially no money. So titanium nitride came as a great surprise and a wonder to us because it looks like gold. So the optical properties are very similar to that of gold by titanium nitride used for drill bits. So it's extremely tough and abundant and cheap material. And what came as extra bonus, it is CMOS compatible. It is already in the CMOS lines. It's used as a gateway and a barrier. Extremely nice material. Biocompatible, by the way, because I'll be talking about biomed as well. And its melting point is almost 3,000 degrees. Looks like a fantastic material to use for applications in photonics, nanophotonics. We know now how to grow it, how to do nanoparticles, and how to transfer it on any substrate, including flexible. That would be very relevant to applications for optical metaskins. Actually, and that's not all of it, because you can look at so many different compounds and so many different elements that are actually, they do look like metals, but they are not. So we call them either semi-metals or intermetallics. And they would all offer their benefits for different applications. Okay, let's look at some of the practical applications. As I already said, the advantage of this, we call them plasmonic ceramic materials because they're really, really stable and tough, is that now we can use them for applications where things are heated up. Well, first of all, of course, high temperature applications. So what are the high temperature applications of photonics? Energy, for sure. So in energy applications that I will show you, it's extremely important that you go away from the traditional metals. Well, look at this picture. So we had a gold and titanium nitride nanostructures that we heated up only until 800 degrees, and it already completely destroyed. Or for applications for high power lasers, or the gold structures would be totally destroyed, even at very moderate laser powers. So another example would be harsh environment sensing. Now, if we look at, say, the whole gas and oil industry, there is no optical component that could go near a drill bit. What about a hot engine? How do you monitor the temperature of the hot engine? Well, optics is fast. Optical fibers are wonderful. There are many optical fiber sensors, but it will melt. It's glass. So nothing could go near except for ceramic materials like that. But even if we talk about applications that are operating at room temperature, such as data storage or data recording, I will show you that you actually need to have very stable materials to enable the next generation of data recording, or to that matter, photothermal therapy and other biomedical applications. So let's start with the first example. So we'll just go very quickly through the applications. And the first is photovoltaics. I already said that, everyone knows a solar cell, and everyone knows by now that there is a fundamental limit of for the just single junction PV cell. It's under 34%. So ultimately it boils down to the fact that when you have a solar panel, a lot of light is lost. So you're losing both low energy and high energy photons. So what would be much better approach is to design a specific absorber which actually just take the broadest spectrum of light you have and absorb it all. We can do it in optics with matter surfaces, but the problem is that when you absorb that much light, you're just heating things up. That's the most efficient way of doing that. So you heat things up until very high temperature, and then you re-emit it in a very special way to match with the PV cell. So theoretically, you can go up to 85%. Fascinating. And the thing is that since the operational temperatures here of your absorber would be around or above 1000 degrees, you need only ceramics, and ceramic would be the answer. So we actually demonstrated that using titanium nitride, you can design such very efficient both the emitters and absorber designs. Okay. It's not only solar. So for us, being technology-driven very much at Purdue, we are thinking about applying this technology or this idea for waste heat harvesting, for the portable power generator, where actually the energy does not necessarily have to be sun. It can be just a fuel burning, right, or the chemical energy, or maybe even radioactive material. So it would be very important to be able to actually construct such a portable power generator, and that's what this technology can offer. Well, we are back to information technology. We cannot just, leave it. But undeniably, as I said, we are after denser and denser information packaging. So we all remember we went from CDs to DVDs to Blu-rays, and it's all because we are shrinking down the size of the each pixel that we are recording. So the next step, as many companies believe, including in Western Digital, is a heat-assisted magnetic recording. And in order to enable this technology, essentially, what you have to do, if you want to reduce the size of your bit, it's tough, because the smaller the size, the more instabilities. Your magnetic moment is always flipping. So if you want to make it stable, you have to use high coercivity materials, and writing temperature should be high. So now, how do you heat your things up here on a scale of 10 nanometers? Only optical nanoantenna can do that. So you are reaching the temperatures up to 500 degrees C here by using so-called near-field transducer. This same optical antenna that I talked about. Now, look at this. 500 C. Remember what I said about gold? Gold will actually be destroyed. And by the way, the Seagate technology and Western Digital, they have patents on nitrides developed, and we were developing them back in 2010. And I'm proud that I had an interaction with the company, not ended on the, my name is not on the patent, but that's another story. But the Seagate actually owns the patents to use nitride materials for next generation of data recording. Biomedical application are also quite exciting, because we can think about applying this heating capability to, for example, shine the light into the nanoparticles that are sitting on the cancer cells and just destroying them thermally. So it's called hyperthermia, when cells are dying because of the simple temperature increase. So we can think that this would be the best way to kill the cancer cells, because there is no side effect, it's just thermal. You can also think in line with what John Rogers is doing at Illinois with a transit electronics. You can think about transit optical components that have embedded nanoparticles of titanium nitride. You shine the light on them, you destroy them. Security and safety would actually benefit from this, as well as targeted delivery of drugs. Okay, so I talked about nitrides enough. One thing I want to mention here is that we went further in exploring different material classes, and another wonder is actually transparent oxides. So those working with electronics or transparent conducting oxide is a special class of material. They are transparent, look like a window glass, but they conduct electricity. So very counterintuitive material, because it is somewhat metallic, somewhat conducting, but it is transparent as well. So the reason for this behavior is actually, indeed, it acts as a metal, but very weak metal. It has a little bit of freak areas, but it would be enough for us to see the plasmonic response there. And that's what we have developed at Purdue. We are using doped zinc oxide, which is well known and well used for decades now for display panels and for flexible electronics. And we are doping it so high that we have enough free electrons to actually excite those plasmonic resonances. The best thing about oxide that we have recently discovered is that we can switch and tune their properties on an ultra-fast scale, both electrically and optically. You have your oxide, or you have your device, you shine the light, you switch it on and off. So ultimately, for all optical systems, that would be extremely important. So now going back to the circuitry that I started with and I'm returning again and again. So using nitrides and oxide, we demonstrate that indeed you can do the same things that people have proposed in plasmonics to do with gold. And we have also demonstrated the design of the optical modulator that has a component size of around 100 nanometers. So we are really getting close to very tight packaging of the optical components. So here, what I want to say that the press release that we go out on Thursday still contains the conventional materials, but our next step is actually to do this with oxides and nitrides. The logical steps from here would be to ask, what will happen next? Because we always have to look further, right? It's what you're doing now is great, but what will happen in 5, in 10 years? Well, if we look at the variation of the, let's say, a Moore's law, then you say that by the year of 2017, which is, by the way, past year, we should be down to 1 atom per bit. Well, you can say, well, it was an overestimate, but not much, because a lot of people are going quantum, and you cannot deny that the next revolution in technologies will be quantum. I am proud to be part of the preeminent team of quantum photonics, led by Professor Chris Green, Vlad, and Andy, where we are trying to merge the ideas for quantum optics as it was achieved and developed in the optical community for decades and bring them into devices and on chips. So the whole idea behind the next technology revolution is really that you go from storing numbers as 0 or 1 into something completely different. You go into something that we call the superposition, because now you can actually have a superposition of 1s and 0s that allows you to process many inputs in parallel. So we are, I don't have time to talk about it. Maybe some of the upcoming seminars can be or should be on quantum, because it's really one of the most exciting things happening now. But we are trying hard to investigate both materials and approaches and designs and utilize the advantages to merge the best of photonics, electronics, plasmonics, and quantum optics to actually bring photonics into quantum chips. Okay, and as I promised, in addition to quantum, which is way ahead of us, but we have to be very active to get there, what is happening now and what is really technology-driven to me is really a metasurface research. So as I mentioned, metasurfaces, you can think of them as a monolayer of this optical materials. You just, throw this nanoparticles on top of a transparent substrate, and you can create very advanced optical skins. So the whole idea behind metasurfaces is that actually now you can replace all bulk optics. Now we started with lenses, right? And we realize that we are still using lenses and mirrors and the bulky components. Well, it might be now changing. So this is something that will definitely go into the next textbooks. And we have to teach next generation of engineers to appreciate that you can achieve now all the optical functionalities I talked about, refraction, reflection, by ultra-thin, nanometer-thin flat optical components. So we are thinking about reconfiguring lenses. Not only they're very thin, you can apply voltage and change it very fast. Dynamic holograms, light sources, novel light sources, sensors, and so on. Just to give you a flavor of things that we are doing, and we have already shown. So at Purdue, in collaboration between myself, Alex, Kildashif, and Vlad, we demonstrated there was a color hologram that is extremely thin, CD spectrometer that, for example, have tremendous potential and applications in biology and pharmaceutical industry, because it can distinguish between the different chirality, which is extremely important in pharma, for example. Replacing standard optical components such as lenses and wave plates, using it for lasing and also for radiation engineering that paves the way to novel light sources. So one of the fancy things recently is, of course, graphene. So just to tell you that we are not missing out on that one as well. So we are looking into how we are utilizing two-dimensional materials in applications for Metasurface. So this is just an example because it's a beautiful snowflake. And hopefully we will not see a snowflake before the next winter. But the snowflake is designed such that we can utilize the properties of a very thin two-dimensional graphene sheet that design a tiny and extremely broadband photodetector. Now, the very recent advancement that came from collaboration between Purdue and Stanford, so led by Vlad Shalaev and Mark Brun-Gessman, Stanford, is actually to enable a whole new technology with Metasurfaces. Now, I don't have time to go into details, but I just want to say for those who are a little bit into phased array optics on how the beam steering is done. So now if you want to move your beam like this, you have to do certain things at the interface, and normally you would changing the phase. So what those guys suggest is actually the brilliant grad student of Vlad, Amr, suggested that you can instead use a frequency arrayed optics, and this will allow you to actually go beyond the speeds that you could achieve using any other means for actually scanning your beam. Now, where are we using the scanning of the laser beam? Well, I would say pretty much everywhere now. We are, well, starting just from scanning and 3D printers for remote sensing, mapping, biology, lidars, and of course, autonomous vehicles. So every time you think about the technology of the future, you want to send the light beam and scan it as soon as you can. And this technology will actually let you go orders of magnitude less and the steering time with very nice characteristics. So what's the future of flat optics, and what are the applications that I haven't mentioned thus far? Optical wearables, Internet of Things. We are going to face a point where whatever is developed with electronics, and again, John Rogers is the leader there with electronic wearables for that monitoring your health. So in sports and medicine, it will go optical for sure because it's faster and more compact. Smart glasses that, well, forget about this really heavy night vision goggles. Maybe next generation of smart glasses would look like this, so that it would be done all optically. Real-time holograms, augmented reality. You can have your glasses that actually project some real-time holograms and you can still see through. So smart windows that actually combine the functionality of energy conserving system or holograms and be as a screens. Smart skins for vehicles as well. So you can think about combining the communication, sensing, camouflaging, and other functions in one. I already talked about biomedical applications and contact lenses. That's a new generation. That's so widespread that it's hardly new technologies that can enter there. Well, it can. Forget about lenses, as I said. Now it's going to be ultra-thin, nanometer thin skin that you can introduce instead of lenses as well. Food safety, harsh environment sensors, and also art, visual arts, and design. And this is the area which I'm very excited about, and I'm pushing for photonics for arts and design in my journal with Optical Society of America. Okay, we are part of Discovery Park, and it's all possible because we have a great team great facilities, but also because we are leveraging on big initiatives. So whatever is happening at Purdue, it really brings together so many different disciplines, and there is no more single discipline. So we are involved in Big Idea Challenge, a brilliant initiative by Thomas, where we are testing photonics for food safety. We are leveraging on preeminent teams. We are looking into how we can push for photonics in life sciences, combining with big data if we are using it for real-life applications, and of course, security. I have to do a lot of things here. And for all the students and the team collaborators and former members, support from different funding agencies. The biggest thanks, of course, go to all the postdocs and students, because they are doing, not only they're doing all the work, actually the new and brilliant ideas are very often come from our young colleagues. So with that, I will leave you with the potential impact of this technology. And my biggest thanks for you for coming here.
Well, that was enlightening. Dazzling is a better term. So, someone who is competent to ask a question, please lead off.
Yes.
So on your previous slide, you mentioned Professor Alou at Texas A&M. I know his big thing is for camouflage. I was wondering what collaboration you have with him on that.
Yeah. So I had an strong collaboration with Andrea, and what we really did there is to apply concepts of matter surfaces and use the new materials to actually realize them. Now, I haven't worked with him on like camouflaging, but because this is like a niche application. But what we did is really to show that by using new materials, you can you can create ultra thin components that would replace bulk optics in, every optical lab. So specifically, we did wave plates. So, you know, the wave plate is a very fundamental optical component that can rotate polarization of light, and you use it to control propagation of light, essentially in every lab. So by using oxides, you can make it ultra thin. It would be semiconductor-based process. There are no metals, and there are, you know, multiple benefits of that. So that's, our Muri project, actually, where we did this is over, but definitely not the collaboration. Andre is leading a big center on photonics now in New York City, and we'll go there.
I have to ask you the science fiction question. You talk about metasurfaces and metamaterials and camouflage. So are we one day going to be able to build a spaceship that can cloak? Are we going to get to start?
Well, like there are a lot of discussion about cloaking. And when I was preparing this talk, I said, I asked Vlad, I think, what do you think I should not that cover, and what is the most resonating or, you know, mind-boggling thing? And then he said cloaking. I said, well, maybe not, because there was so much hype around the Harry Potter thing that at some point, and I say what Vlad would normally reply to questions like, can you cloak, you know, a building or something later, or a vehicle? He would say, you know, we did a lot of cloaks because it's a beautiful science, and we don't care whether it's going to be used or not. It's there, and we are proud that we did studies on the cloak. But when it comes down to practical applications, that would be too challenging just to have a vehicle and cloak it. But with this said, you can still use this technology in a modified version for different things. For example, not really cloaking the object by camouflaging and making an object appear like something else can be a real thing. For example, the stealth technology, like for others, it's similar technology. So if you know your operational frequency range, you can do this. But in the visible light, if you want to cloak an ugly building, probably not. So it's better not to build ugly building. We can cloak you. Well, again, if it's if you have a limited frequency range, let's say if it's night vision, or you're just, this is 10 micron, I want to stay here. Yes, then you can do interesting things there.
You mentioned the negative epsilon materials. What about the near zero? I saw that on one
Yeah.
slide. What do you see as the promise of the epsilon near zero?
So epsilon near zero materials this is the next chapter in the whole optics and the optical devices. So if we open the textbook that we have now and we use to teach our students, there would be a chapter on how light interacts with transparent materials, so dielectrics, and there would be a chapter of how light interacts with metals or conductors that are reflecting light. But there is a realm in between when the material has zero refractive index or zero epsilon, and which is absolutely unexplored. And it will lead to, well, let's say rewriting of some of the very fundamental laws. So we have to rethink how light would behave in such a material. And I'm sure we will be able to design and utilize these materials. So one of the greatest things about oxides that we introduce and we study is that oxides do act as epsilon near zero materials in the near IR. So the way to think about it, remember what I said about oxides? They are transparent, but they're also conducting electricity. So they are somewhat in between a metal and a dielectric, which means that there is a frequency range, there is a wavelength at which this material has a very, very low index of refraction. Now back to applications. You can have different effects that are associated with extremely low N. Now, very advanced wavefront shaping can happen, or radiation engineering can happen with epsilon near zero materials. If you can think in a very simple terms, if you have a light source or emitter, and you put this emitter on the epsilon near zero material, and it's surrounded, the down half plane is epsilon near zero. Just the Snell's law will tell you that everything will be reflected upwards. So you can really engineer the emission from your emitters in a completely different way. That's one thing. The second one is going quantum. So if your refractive index or your epsilon is near zero, you can say that your wavelength is so large inside the material. So inside the material, if you want to find the wavelengths, you take the wavelengths and divide it by refractive index. And if refractive index is very small, your wavelength is very, very large. So if you're having two quantum objects really far from each other, under normal circumstances, there is no way they will talk to each other. There is no way to couple them. In epsilon near zero, you can actually couple structures that are really far away, optically far away from each other. So you can design quantum systems that will be tolerable to displacement or where the system is. So you can expand the strong coupling regime far beyond the normal near field scale. So that's one of the interesting things. So radiation engineering and this, strong coupling, we consider being one of the most interesting directions. That was too scientific, so yes.
I will preface this by saying I am not an optics or physics person. So I see you driving to something smaller and smaller and smaller, which over here in the aerospace industry makes me very, very happy. But you said that it also gets hotter. Now on my macro scale, is your getting hotter actually making my macro scale hotter? Am I going to have more heat that I'm going to have to figure out how to get rid of?
Well, if you are heating, so take the data recording process that I mentioned. So indeed, what is happening is that by using this tiniest metallic nanoparticle. You couple light down to this hot spot. You raise the local temperature in order to do whatever writing you are doing. And the whole design of the structure will actually depend on the heat transfer as well. So it's as much electromagnetic or optical problem as the heat transfer problem. So you have to, in a device like this, you will have to take into account the heating effect and how to actually design the heat flow as well. So yes, these are coupled, and heat transfer at the nanoscale is yet another fascinating problem that people are working on now.
Building off that question, does heat transfer work differently on the nanoscale? It's not just the heat equation anymore? Or?
Well, it's different, yeah, and you can. Well, some people say that you can even go beyond of what you would do with a classical heat transfer. And there are many questions in this field remaining, but the short answer would be yes, it's different.
So while you're trying to quote Tomas, where do you think the first applications will be seen amongst your...
For metasurfaces? Yeah. Well, we already saw the first one. The first startup company, which is very successful, with investment and, I believe, acquisition from ZEISS. ZEISS is a leader for making microscopes and microscopy systems. They're utilizing metasurface lens instead of objective. So replacing conventional bulk optics with thin films is the first step, and it's happening now. Recently, I saw also a press release on making contact lenses. They completely different way, and for some people with astigmatism, for example, like myself, lenses tend to be thicker, and you can feel them in the eye with all this awkward things happening. So you can do it ultra thin. Special light modulators would be the next step. Well, and hopefully beam steering. Yeah, we are excited about LiDARs and autonomous vehicles. So I'm sure this, someone has to jump on it right now and make it happen.
Any other brave people? Well, I know we can prevail on Dr. Boltasseva to stay around for a while, and I hope many of you will too. And the question you weren't bold enough to ask her in front of the rest of us, you can sneak up and ask her now. But that was really spectacular. And
Thank you.
What a terrific story you allowed together. I thought it was awfully nice that you shared that part with those who weren't already aware. So we're very proud. You're young with lots of scientific runway ahead of you. We can't wait. I'm thinking maybe some future colloquium, someone will put up their picture on the Nobel list. Thank you very much.
Thank you. Thank you.